Hey, welcome to the podcast.
Thanks for having me.
So I was reading about acids and bases, right? And I hit this thing about pH, and it just says negative log of hydronium concentration. Like, what does that even mean?
Okay. So pH basically just tells you how many of these hydronium ions are floating around in your solution. But here's the weird part. It's a negative log. So when you have more hydronium, the pH actually goes down. Low pH is acidic. High pH is basic.
Wait, that's backwards from what I'd expect.
I know, right? But there's this thing where each step is a 10-fold change. So pH 3 is like 10 times more acidic than pH 4.
No way, really? Tenfold?
Yeah, and water is a perfect example. They said there's one hydronium ion for every 10 million water molecules, which comes out to pH 7, totally neutral.
Okay, and then they said pH and pOH always add up to 14. So like if I know one, I know the other automatically?
Exactly. That's the handy rule for water at room temperature. If pH is 3, pOH is 11, you can track acidity either way.
Oh, and strong acids versus weak acids. Strong ones just totally fall apart in water and dump all their protons, right?
Yeah, they dissociate almost completely, so you get tons of hydronium ions. Weak acids barely break apart, so fewer hydronium ions and higher pH. That's why concentration and strength are totally different things.
And when you mix a strong acid with a strong base, they just cancel out? No explosion or anything?
Nope. They form water and a salt, like HCl and NaOH make water and table salt. That's it. Pretty boring, actually.
But then they get into redox reactions and the wording was confusing. They're like, sodium is the oxidant and chlorine is the reduced. And then they're like, wait, no, that's backwards. So which one's which?
Yeah, that part was messy. But the rule is simple. Oxidation is losing electrons, reduction is gaining electrons. Sodium loses an electron, chlorine gains one. So sodium gets oxidized, chlorine gets reduced.
Impressive. They also showed this trick with oxidation numbers in sulfuric acid, like oxygen adds up to 8, hydrogen to -6, so sulfur has to be +6. That was actually really practical.
It's a fast shortcut. You just remember the common ones. Hydrogen's usually +1, oxygen's usually -2. Add them up and solve for what you're missing. Works most of the time.
Can we jump to atoms for a second? The material says everything's made of atoms with a nucleus and electrons in shells, but then it gets weird about quantum mechanics, like electrons aren't actually orbiting.
Right. So classically, you'd think they're like little planets orbiting, but that's wrong. They're more like clouds described by these things called wave functions. But for now, just think shells and subshells and you're fine.
I liked the periodic table part. The group number tells you how many valence electrons you've got in the main groups, and noble gases have full outer shells, so they don't need to react with anything.
Exactly. Most of chemistry is just atoms trying to fill their outer shells comfortably. Lewis structures show those valence electrons and how they bond.
And that's why isomers are a thing, right? Same atoms, different arrangement like graphite and diamond are both carbon, but totally different properties because of how they're structured.
Yeah, the bonding geometry changes everything. Then they ranked all the different forces: ionic, covalent, metallic, hydrogen bonds, van der Waals, strongest to weakest, which explains why some things melt at different temperatures.
And with states of matter, solids are organized in low entropy, liquids are more use, gases are chaos, temperatures just average kinetic energy, entropy's disorder. That's where Gibbs Free Energy comes in, right?
Yep, they give you the formula delta G equals delta H minus T times delta S. If delta G is negative, the reaction happens on its own. So even if something needs energy to happen, if entropy increases enough, it can still be spontaneous at high temperature.
Like ice melting. It takes energy but increases entropy. So above freezing, delta G goes negative and boom, ice melts.
And catalysts to speed things up by lowering the activation energy without getting used up. That explains enzymes, industrial stuff, all of it.
Oh, and stoichiometry. You can't just weigh things in grams. You need to use molar masses to get moles, which is like a counting unit. 2 moles of hydrogen for every 1 mole of oxygen in water.
Right. You convert grams to moles using atomic masses, balance your equations, and boom, conservation of mass. Metals first, then nonmetals, then hydrogen and oxygen are just trial and error until it works.
Bless you. This one issue quantum numbers things. NL, all these letters. They said some guy named Poe said 2 electrons can never have the same quantum numbers in one atom, giggling. Weird way to phrase it, but basically that's the exclusion principle.
Yeah, that wording was quirky. But the point is those 4 numbers define where an electron is. Each orbital holds 2 electrons with opposite spins, so s orbitals hold 2, p holds 6, d holds 10, f holds 14. You fill them in order and boom, you've got your configuration.
And that's why valence electrons matter so much for how atoms react. Electron activity increases toward the top right of the table, which determines whether you get ionic or covalent bonding.
Exactly. Sodium and chlorine are super different, so they form ionic bonds. But water, oxygen pulls hard on those hydrogens, creating this dipole, which leads to hydrogen bonding and makes water this amazing solvent. That's why it boils so high and dissolves everything.
It connects, man. That's what I love about chemistry.
Yeah, once you see the patterns, it makes sense.
Thanks for walking through all that.
Yeah, this was fun.